Okay, today is May the 6th, and it's that time that we have to do a daily challenge before the deadline reach. So today, um, as usual, we have another medium question again, and it's number. Let me check. This is number 109. So this is number 109, convert sorted list to binary search tree. So it's a medium question. It has like 3,000 upvotes, and it's a question under 400. So I will consider it a classic LeetCode question that probably requires some basic algorithm that we need to learn. So yeah, so it's good that today we have the chance to practice this LeetCode question. So let's get started. So first, let us read the question together. Okay, so the question is, the title is Convert Sorted List to Binary Search Tree. Given the head of a singly linked list where elements are sorted in ascending order, convert it to a height balanced BST. Okay, so for this problem, a height balanced binary tree is defined as a binary tree in which the depth of the two subtree of every node never differ by more than one. Okay, so here is an example. How many examples we have? We have 4. Okay. My cat is here. So let's check the first example. So it's a linked list, and it's a sorted linked list. So it's -10, -3, 0, 5, 9, and we need to convert it to a BST. So, and the BST of both sides, or I should say for each node, the left child and the right child, their depth should not be differ by more than 1. So they are either the same or by 1. Okay. And they are sorted. Okay, and then the example 2 is just telling us that if we it could be a empty list, and then we are going to return an empty node, I believe. And then the third one is it could be a single uh, sing, length 1 linked list. Then we have to return a single node. And example 4 is just another easy example, which you have a sorted 1, 3, and then I guess, yeah, you have 3 as the root and 1 as the left child. Okay, so let's see how they so they give you 2 class. One is the list node, one is the tree node. So your input is the list node and your output will be the tree node. And from here we see the representation of this BST is root, left, right, left, null. Okay. Where's the 9? Okay. Okay, so actually for example 4, you can choose either 1 as root or 3 as root. It doesn't matter at all, I think. Okay, so the constraint that we have is the number of node in head. What is head? Head is the input linked list. Is in the range from 0 is the example 2 to 2 times 10 to the 4th. So it's 20,000. Okay, and the range of the value is negative 10 to the 5 to 10 to the 5. So the range of the value is pretty big, and it contains a negative value. Okay. So I think this is pretty simple, right? So for BST, which is a binary search tree, you have a root, and then your left child will always be smaller than you, and then your right child will be always larger than you. So do we have duplicate record? I guess that doesn't matter, right? And it doesn't say. It only said that it's sorted in ascending order, and it didn't say that do we have duplicate number or not. But I don't think that matters, right? Or for a BST, we are not supposed to have duplicate number. That's what I think, right? Because a duplicate number means that you can either put that into the left node or right node. But I think it won't matter. So yeah, so the trick first, I think, is that we can do a recursive call. So for each call of the sorted list to BST, we return this as the root, right? We return a tree using this as a root. So the trick is, for every recursive call, you just find the node in the middle, and then so for all the right hand side, you recursive call our function again to get a BST, and for the node in the right hand side, you recursive call the BST to get a BST, to get a tree, and then assign the left hand side to become your left node, left child, and then the right hand side to your right child, and then return the middle node. So this is supposed to be really simple, and because you always use the node in the middle. So for example, this has 5 nodes, so if we get the middle, which guarantees us that the right hand side, the right child and the left child will differ by less than 1, right? And if this is a list with even number of nodes, then it doesn't matter if we, for example, if we don't have this 9, and it doesn't matter if we use -3 as root or 0 as root. Our left child and right child will always only differ by 1. So, and the other thing is, we already know the algorithm of how to get the middle element of a linked list, right? So we just have two pointer, a fast node and a small node. So the fast one always jump 2 position, and the slower one always only jump 1. So when the faster one reach to the end, the slower one is in the middle, right? Okay, so I guess that works. So let's start coding. So first, we have this linked list. So we probably, like I said, to find the middle, we need to have a list node called slow, and we also need a fast. And how do we initiate? We probably can initiate it as head, both as head, right? And then we need to do a while loop, while like fast dot, so what's next, okay, fast dot next is not null. So then fast equals to fast dot next. Okay, now here's the trick. Let's see. So say that we have 5 node, right? And we have 5 node. And then we start with this one as the first one. So both slow and fast are this one. So the first while loop, we increment fast by 2 and then slow by 1. So slow will be the second one, fast will be the third one. And the second round, we increment fast by 2 and slow by 1. So then we get out of the loop because the fast next is null, and now slow is in the middle. So then we use slow as the node that we are going to return. But what if we have 4? If we have 4, then both start with the first one, and then the first while loop, fast is in the third, slow is in here. And the next round, when we increment fast, and fast reaches to the end, and we cannot increment one more, then slow stay in here. So slow can be or cannot be, can slow be the root that we return? Yes, because now we have left tree length 1, right tree length 2, and they are only differ by 1. Okay, so that's what we are gonna do. So we first increment fast by 1, and then we increment, and then we check if, I know this is a little bit stupid, but this type of thing always confuses me. So if fast the next is not, is null, or is null, then we break. Otherwise, we increment fast again and slow. Okay, so that should work. Well, maybe later if my mind is clearer than now, then maybe we can make this part looks more like elegant. But for now, let's settle with this. So when we break out of the while loop, in theory, the slow node is the node that we are going to return, right? And the slow dot next is the beginning of the right hand child, and the head is still the beginning of the left hand child. So let's do it. So what we are going to do is that I will initiate a tree node. Res means that this is the one we want to return. And what is the, so call it with the value. Okay, so new a tree node with the value of the slow dot vol. Is that vol? Yeah, it is vol. Oh, well, anyways, and then maybe we can use this constructor, right? Maybe you can use this constructor. Okay, so what's left? So left child will be recursive calling this with what? we still had, right? And then the right child will be recursively calling this with slow done next. But wait a sec. For this to be the left child, we need to set a null, right? So this might not work because we need to cut this linked list and make the one prior to the slow point to null. So it's probably better that we tweak the fast and slow logic so that when we exit the while loop, slow down next is the node that we are going to return, so that we can set the slow down next to null to cut off the linked list in the left. Right? So let's tweak the logic. Oh god, I need to rethink the logic again. So when fast jump 2, slow jump 1, and then we fast jump 2, slow jump 1. Yeah, so I better let slow stay as the last one of the left hand child. Right, so we probably can move. So what if 4? So 4 this works, right? For this works. So for 4 of them, when fast jump 1 and cannot jump again, then we exit out. But 5, when 4, so it might be easier we have a pre-head. So everybody start from the pre-head. But do we need to, okay, so how to write this code elegantly so that it works for both even and odd? That's the thing I need to work on, right? Because I definitely need to check. Okay, so maybe I can directly check if we jump, if here we don't jump again. Right, so if we are 5, so when fast jump here, but slow will jump to the middle one. And the middle one is the one that we need to return, but I can't cut off because I need the previous one. So how do I make the slow stop at the previous one? That's okay. I'm gonna make it really ugly. Just that for now, I know later if I check the solution, the solution will, other people's solution or the official solution will look better than this. But for now, I want to stop the slow pointer so that the slow pointer's next point to the node that we are going to return. So if so I'm going to do this. If it's not null, then we increment this. And then oh my god, it's really ugly. I don't like my code here, but let me fix this later. I mean, for now, I just want to make sure that the slow is point to the one that we need to return. So okay, so I will have this. Okay, then let's not do this. Let's do this. So I will have this dot next, and then after I create the one that we need to return, I cut off this first linked list. So I point this to null. Oh, not yet. I need to call this first. So I need rest the right equals to this, and then I cut it off, and then I have rest the left equals to head. And this should be slow down next. Okay, so now I am not even sure, do we always have the slow down next? Let's see if we have 3. Okay, let's say if we have 2 for this example, right? I have fast, I have slow, all start with 1. So when the fast dot next is not in null, then I increment fast, and then now it's null, so we don't increment slow. So now slow is 1, fast is 2, and then we break out this, and then I made. So yeah, I will always have slow down next in this situation. But how about we only have one node? So if we only have one node, fast.next is already null, so both stay as 0, and then now I will have trouble with this, right? Because I don't have slow.next. But that's not a problem, because remember, this is a recursive call. We haven't defined the ending situation. So the ending situation is that if we pass a null pointer or we pass a single value linked list or single node linked list, right? So we can deal with that in here. So if head is null, return null. And if head dot next is null, return new tree node head wall. Okay, I think this works. Although I believe somebody else will be able to just write this as the ending condition, so that it will naturally assign null to the right and null to the left if the input is only one node for a linked list. But for now, I can't wrap up my head with something that's elegantly that way. So I think for now, this works for me. Okay, so who clicked my... Uh-oh. Oh, I have issues with my keyboard. So... I have issues with my keyboard or my mouse. Is something clicking my mouse? Are you clicking my mouse? My cat. Oh yeah, it's my cat. Oh my god. Hold on. Let me turn off this. Okay. Now I'm back. Okay, cool. So I guess that's it. Right? So I'm guaranteed that when we reach this part, the linked list will always at least have two nodes. So we always have slow.next.next. And then we always can cut off this. Let's try to run the test case. Compile error. I always have compile error. What's wrong? Okay, this is this. Oh, did I forget to return? It looks like it works. So the second one is, the third one is okay. So let's try different test case. It should work. It should work. So let's try something even. I think the value inside here, it really doesn't matter, right? Because as long as it's sorted, right? So actually we can just try it, because it only matters how many elements we have in the linked list. It doesn't matter what's the value as long as it's sorted. So let's try 1, 2, 3, 4, 5, 6, 7, 8, 9. And then let's try another one with, so this is the odd value, and let's try another one with even value. Runtime error. So we do, oh god, I have a typo. Looks like it works, so I think it's probably good for us to submit it now. Okay, it works. So let's see the result. So what's the time complexity? So I think, okay, so this is really a, I guess, not that complicated of a problem. So everybody's time complexity is similar, and the memory usage for mine is not bad. Maybe because my runtime is slower because I directly use this linked list. So what's our time complexity? Because first, of course, we know we are building a tree, right? So for building this tree, we need at least log n, right? Second, because for the log n sorted list BST call, for each of the recursive call, we traverse the entire tree again. So it's like, think about this graph or this tree. In this level 0, we traverse entire element. We traverse in like all the 5 elements, And in this level, again, for this we traverse this part. For this we traverse this part. So it's again the second level we traverse all the 5 elements. So in each level we traverse each n element again and again, and there are log n level, so the time complexity should be n log n. And the space usage, because we are doing recursive call, so it should be n, right? Because every time, every call, we return one node, and you see there is 5 node. So to create a tree node based on the least node's value, we need to call once the recursive call for each node in order to get a value. So the recursive call system stack usage should be O of n, which is not too bad, but not too good, I think. Okay, then let's try to see the solution to see if our solution is correct and how they do it more elegantly than ours or than mine. And also to see if our time complexity is correct. So recursion, this is what we use, right? So let's see. So yeah, time complexity is n log n. And what's the space? Space is log n, but it should be O of n, right? Since we are restoring the always added space complexity to stack that counts with. Yeah, so if you count the stack, the system stack, it should be O of n, right? Although the height is O of log n. Yeah, so why? But the question clearly is that we need to maintain the height balanced properly. This ensure the height of the tree. Yeah, I know the height of tree is this, but for a recursive call, okay, I was wrong. So yeah, also for the recursive call, we do need to call this function recursively n times. But the stack height, the stack that we use should be only the height of the tree. So yes, actually the space should be log n, because the longest height of the tree is log n. So we only use a stack of size log n, and then we return, although we call it n times. Yeah, so I was wrong. So yeah, my space complexity analysis was wrong. So this is correct. It's based on the height if you want to count the system stack. Okay, so what's the recursion and conversion to array? You can get time complexity down by using more space. Oh yeah. Okay, so I guess they first convert the entire linked list to an array so that you don't need to traverse the linked list, right? For array, each element you can just use constant time to access it. So once you change it to an array, your time complexity is lowered to O of n, right? So yes, and then your space complexity is O of n because you have an entire array. Yes. Good. Oh, hi, hello. Which area of security is most difficult? Which area of security is most difficult? I honestly don't know. Thank you for asking questions, but I don't, because I am a software engineer wannabe. I'm not a software engineer, so yeah, I'm sorry. For now I'm just like practicing algorithm questions. I don't know about security that much. But thank you for asking though. Yeah. So I don't know. It seems like every part of the security is difficult for me because I don't have any experience. Yeah. Thank you. Okay. So let's keep continuing looking the third and the I believe web or Trojans. Which one is more difficult? Do you mean difficult for you to prevent getting hacked? I think of course the web is more difficult, right? Because Trojans only work on your local machine, and yeah, so most people will just use antivirus. So the scope of a local machine, security problem on a local machine is way smaller than the scope of the web security, right? So that's what I think. Then what do you think? You can tell us. Okay, so what is the approach 3 though? In order simulation. And so we are doing an in order traversal. Yeah, I know it's, yeah, of course, if you do an in order traversal on a BST, it will become a sorted array. But to reverse it, it's sort of like, it's a little bit hard. How about finding the web bug versus reversing? Oh, you want to reverse the Trojan? I don't think normal people have the ability to reverse it, right? You either just rely on the uh, antivirus software to help you reverse, but if it's a ransomware, you're probably out of luck. And then a web bug, if you're talking about a bug, yeah, it depends on what kind of bug that you are talking about, right? A web bug, like which kind? Like SQL injection? I think that's already pretty common that everybody who is doing web developing know how to prevent SQL injection, right? I think. So it depends on which bug that you are talking about. But you are like in a, if you are maintaining a like web API, then that's another story, right? So do you want to put your API out in the internet, or you have a gateway so that you only let your intranet access the API, not your front end, directly access API to your back end? So yeah, I think it depends on what kind of web bug you are talking about. So yeah, but I don't have much experience on that, so I can't really answer. Sorry. Okay. So yeah, I still don't understand. There are much less SQL injection nowadays, but people still find them. Yeah, because if you have a web developer like me who don't have experience, then I might develop a website that's easily hacked by a SQL injection, right? So yeah. Okay. So let's see. Let's see. I don't quite understand if they are just doing a reverse in order traversal. SQL map? What is SQL map? Do you do SQL map? I don't know what is SQL map though. Sorry. What is SQL map? And find size. So they find size by traversing the entire array. Okay. A tool. I never use SQL map. Yeah. Maybe I'll Google it later, but no, I never use SQL map. And then we have find size. Find size, and head is head, and you convert this to BST. Left and right. And then you got the middle, and then you convert. I don't get it. What's the difference between recursive call and this one? You have the start, you have the end, and then you create a node on the head. So where do you have the head? When you are doing the recursive call to convert this to BST, is your head or your head is a global variable? Oh my god. Okay, and then head plus plus. Okay, so if someone was the guy who found most of the bugs or hacks at a hacker store, what would you guess it's his potential salary? Huh? Salary? If someone was the guy who found most of the bugs for the hacks as at a hacker store, potential salary? I don't know. I'm not in this industry, so I actually don't know how this industry is paid in North America. I don't know. So do you mean by like when company hire those white hat hackers, or the hackers? Okay, black market. No, sorry, I really don't know. I mean, you are asking question that I can't answer, and I hope that you can directly give me the answer because I can probably learn from you. Yeah, but as you can see, I'm just barely only practicing algorithm question here on the internet. So yeah, I don't know. I don't know about hacking. Yeah. So this solution troubles me a little bit because you have the head start from the first one, right? And then for each one, yes. For, so when they're in the initial call, you find the size of the list. You have the head as the first one, and then you call the cover from 0 to the last. And then, for example, for the first call, you have mid as this, and then you convert your left, and then you convert your right, and then you return node left, and then node right. Maintain the invariance mentioned in the algorithm. Yeah, well, this they say it's mimic to the in order traversal, but it's a little bit hard for me to understand. Okay, weird how the guy who organized it make the most money, and I guess the best seller. You are confused me. I don't know about the hackers market and how they got paid or anything. Yeah. Okay, so I guess that's it for today's daily question. Um, yeah, the only thing I don't quite understand is this in order traversal simulation. I mean, I know how to do it in order traversal, but I don't know how they reverse it back to a tree though. So yeah. Yeah, but yeah. So yeah, I will probably read this later again. Yeah, but for me, it's like this solution is also a recursive call. I mean, if they can make it a iterative solution, then I might be interested. But for an in-order simulation, I probably think the recursive answer is probably the easiest to understand, the most intuitive one to understand. Do you study probability theory? No, I don't. If I do, then I will probably practice this in Python and try to get a data science job or data analyst job, but no. What? Suppose a stock has initial price drift 3 per years and what's the probability of the stock? What do you mean? Okay, now you are confused me. So yeah, suppose a stock has initial price drifted of 3 per years and 30 parameter is I don't know what you're talking about. And I don't know why you're asking me this question though. Yeah. Well, yeah, sorry. I don't do probability. If I do probability then yeah, this today's episode will be entirely in Python so that I can practice and to apply for a data science job. But now you see that I am practice it in Java, so I have no intention on getting into the data science market, job market at all. So yeah. So okay, that's it for today's streaming for the daily question. And I will come back tomorrow for another daily LeetCode challenge. So thank you for watching for today, and I will see you tomorrow. Thank you. Bye bye.